Good afternoon.
Hello guys, nice to see you. Hi. Hello everyone. Good afternoon.
Good afternoon.
Hi. Okay. So how are you doing guys after weekend? Ready to work? Yeah, I'm also fine. A bit difficult to start working on Monday, but we don't have choice. Need to accustom. Long week ahead. Okay, so last time we discussed the finished our discussion of the sound waves, and in particularly we discussed the Doppler effect and shock wave, which is formed in atmosphere, for instance, when there is some object which is moving faster than speed of sound. So we considered the formation of this Mach cone and tried to explain how this shock wave is formed. So with that, we finished the discussion of this sound wave topic, and actually we also finished the discussion of big chapter, which is mechanics. So we make a transition now to our next second half of the course, which is thermodynamics and molecular physics. So today we will start to introduce the concepts of thermodynamics and try to understand what is one of the key parameters in thermodynamics is which is temperature. So what is temperature, how we measure temperature, and how some materials, let's say solid materials or liquid materials, behave under change of temperature in terms of their thermal expansion. So we will discuss these questions and proceed further on our next discussions on Wednesday and Friday with the introduction of ideal gas, laws of ideal gas, and so on. Okay, so let me switch to slides. Okay, good, it works. And first of all, we should highlight that thermodynamics studies how temperature and state of matter, it means solid, liquid, or gaseous state, are changing due to the transfer of energy, mostly in the form of heat. And thermodynamics is definitely closely related to some microscopic features and like atomic features of matter. However, it deals with macroscopical parameters, and the most important are temperature and pressure. So we have temperature T and pressure P. So our main focus will be now on temperature, and we can explain temperature as a parameter which provides some quantitative information on the internal energy of the system. And it's a question how we can quantify it. So from one side, we can just touch some objects and by feeling say, okay, this is cold or this is hot. However, that is very subjective approach to measure temperature, and we definitely need some quantitative approach. So one of the options, we need to make some connection between the property of some body and change in temperature. Then if we find such correlation, we can calibrate it for some known reference temperatures, divided in equal steps, and that will be our temperature range where we can measure quantitatively temperature. So one simple approach would be, since we know that solid bodies expand with increase of temperature, if we have some rod with certain length L, then at some temperature T1, then if we increase temperature to T2, which is higher than T1, this rod will experience some thermal expansion. So here we will have this delta L that will be changed in length because of thermal expansion. So in this case, this delta L will be proportional to T2 minus T1, which is delta T. And if we measure for between some reference points, which we will discuss a bit later, we can calibrate such a thermometer. However, what do you believe is the main reason why we don't use such thermometers in practice? Any ideas? Have you seen such thermometers in everyday life or somewhere common use based on thermal expansion of some rods?
No.
Yeah, only liquids we have. Yeah, so there is actually a reason for that, because honestly saying liquid thermometers are way more complicated than this one. It would be just some rod. So why would we are not enemies to ourselves, but we usually don't look for more complex solutions. However, in this case, we cannot use just a rod. Why? Because thermal expansion of solid materials, of course, it changes from one material to another, but it is very small thermal expansion. And to measure accurately this small change in length, it would be a great challenge. So the measurement itself of this accurately, of this small change in length, would be such a challenging task that it overperforms the challenges in terms of developing other engineering other solutions for measuring temperature. So as you mentioned already, most commonly used are so-called liquid thermometers. So liquid thermometer represents some very small tube, like with small cross section, with some bigger reservoir on the bottom. So this is filled with some working liquid. We will discuss a bit more about this liquid. And we have some gradient, like some grading on the tube. So we have marks which denote temperature. So let's say 0, 20, 40, 60, and so on degrees Celsius, for instance. So obviously, how it works, that this edge of the liquid its position is calibrated at 2 reference points, and then we can determine temperature. So first of all, let's start from the working material inside this thermometer. So as you may know, quite often nowadays, it's kind of not environmentally not favorable solution, but in order to get the most accurate liquid thermometer, we need to use mercury. Any ideas why such nasty material, which can cause damage to human health when inhaled, like some vapor, so it's quite toxic material, why do we go for this and put our potentially our health in some danger? Usually if you operate properly with thermometers, don't break them, and nothing happens, but it has potential danger. But we still go for that in order to gain maximum accuracy. So from your point of view, what makes mercury such a perfect material for liquid thermometers? So what is mercury? Is some liquid. Okay, there are some suggestions. Let's see, what do we get? So because it's a metal, yes. Boiling point is high and high expansion coefficient. Yeah, you are close to the point. And first of all, we measure atmospheric pressure with it. Well, we measure atmospheric pressure with it only because it is very heavy, and instead of having 10 meters of water, we can have like 70 centimeters of mercury, or so, because it's much denser than water. So it's just convenience in terms of its density, and it doesn't have direct impact on, doesn't have direct reasons that we also need to use it for thermometers. But you are right, we also use it for measuring atmospheric pressure. So it is a metal. Let's start from this. Indeed, it is a metal. And what metals, what kind of properties metals possess in comparison to other materials? Let's say if you have some insulator or thermal, yeah, not temperature conductivity, but thermal conductivity is the right term, but temperature conductivity could be also understood what you mean. So correct is thermal conductivity. So a high thermal conductivity. If we compare metal and some plastic, obviously metal will have higher thermal conductivity. And that is very important because of the following established measuring procedure. How do we measure temperature? We usually, let's say this is some liquid surface. We immerse this thermometer inside the liquid, and we want it to get into a thermal equilibrium as fast as possible in all volume. We don't want outer part of mercury be at one temperature and then wait for a long time in order to reach the same temperature in whole volume of mercury, which is comprised in this glass tube and this reservoir. So we want to get our temperature reading as fast as possible. And that will be possible only if the thermal conductivity of the measuring active material, let's call it like this, would be very high. And nothing better than liquid metal can deal with this. Since mercury remains liquid until about minus 40 degrees Celsius, so it can be widely used for measuring temperature in under normal condition in atmosphere, because usually we don't have temperatures lower than 40 degrees in the area where human habitate for long. Maybe here in Astana we have a chance to get lower temperatures than 40, but that is quite extreme already temperature. So for most cases in this temperature range, a temperature range from minus 40 up to, let's say, 80 or 100 degrees Celsius is quite sufficient for practical applications. Another feature of mercury, which is important, that it doesn't wet the surface of glass. And what I mean doesn't wet. If you look at, I don't know, some glass with water or wine, you can see at the edge such tiny menisc. So we have flat surface, and at the interface where water contacts the surface of glass, because of watering the surface of glass, it defines how the surface tension of the liquid and surface energy of the material it interacts with defines will be watered or not. So it will, if we have a drop of liquid on top of some surface, and then this drop will make such flat shape, that means that surface is watered by this liquid. However, there is possible that instead we will have something like this. So this drop will be more like some sphere, closer to some sphere. And in that case, the surface on which this drop is located is not watered by this liquid. So as opposite to other liquids, which are commonly used also in thermometers, mercury doesn't water the surface of glass, and that means that we have something like this. We have flat surface and a bit downwards bended edges. And that allows us to define very clear and with high accuracy where is this level of mercury is located. So we need to know it because we measure according to its position temperature. So it's 20, 40, 60 degrees Celsius. If we have some alcohol, which is also used in liquid thermometers, specifically when you need to measure temperatures lower than minus 40 degrees, because mercury already freezes and it will break the glass tube located in. Then we have this watering effect, and the edge of the surface of alcohol is not so well defined optically. So there is some uncertainty within its position because of this menisc that we just cannot accurately measure this temperature. So these are two of the most important features of mercury, which have to be taken into account in explaining the reason why we use it for measuring temperature in liquid thermometers. Another thing that this volumetric expansion of liquids is also quite small with increase of temperature. It's not huge. So the design of thermometers with this tiny tube attached to bigger reservoir is made specifically like this because then even small change in volume will be visible since the tube is very small, the diameter of this tube is very small, and even a small change in volume will result in quite significant motion, like displacement of this interface between, for instance, mercury and some empty space of the tube. Another thing that is actually not so trivial as may look from the first point of view to measure correctly temperature. I will just highlight one of the problems which should be taken into account when you deal with liquid thermometers. There are more, but just one as an example. So you see this example here. We have liquid surface. We immerse our reservoir with mercury, for instance, in liquid, and we measure temperature. We want to know temperature of this liquid, T. Let's call it TL, T liquid. However, not all volume of mercury is located inside this liquid. As you may, like 99% of it, yes, it is in the liquid. However, some small part of this liquid is already in the tube. So here we have this pillar of mercury, which is above the level of our liquid, where we want to measure temperature. And this part of mercury stays at temperature, which is something between temperature of the liquid and temperature of the air, for instance, like room temperature. So in that case, we need to take, there are certain approaches and equations which take into account this tiny effect of active material, active liquid, for instance, mercury, which stays beyond, above the level of measuring environment. And because of this, we get some error which can be corrected. But you should just know about this and apply certain approaches in order to compensate this error. So that's just one example which would be necessary to consider when you need to measure temperature indeed with maximum accuracy. And now we need to tell that there are some issues with liquid thermometers because not all liquids and not in all temperature ranges they expand linearly. So it means that we want for each interval between, let's say, 0, 20, 40, and 60, we want that each distance between them remains constant. So for 1 degree Celsius should be, let's say, 1 millimeter of expansion of this mercury along the tube. However, not for all temperature ranges, they expand linearly, and that creates problems for accurate measurement. That's why for some specific applications, for accurate measurement, like extremely accurate measurement of temperature with for sure linear dependence of parameters which we measure versus temperature, we use so-called constant volume thermometer. So constant volume thermometer is actually a gas thermometer when we have similar structure, but working principle is different. So we have a tube with some reservoir, but it's filled with some gas. So we can write here gas. And we immerse it in some liquid in order to measure temperature of this liquid, for instance. And then we change temperature of this liquid, so we get different temperatures. And then what happens if we have just some gas here comprised in this tube? It would like to expand. However, what we do, we add on top, for instance, mercury, in order to compensate this thermal expansion. So we keep this volume of the gas constant. So volume is constant. Pressure is not constant, because if we increase temperature, pressure will also increase. So we will talk about this in more details a bit later. But and the height of this pillar of mercury, which will compensate excessive pressure because of increased temperature, that will, let's call it H. H will also not be constant, because we will need more mercury, a higher pillar of mercury, to compensate higher temperature in order to keep this volume constant. So in that case, we will have something like this. Here we have temperature, for instance, let's say in degrees Celsius, and here we have pressure. We know pressure because it will be P will be equal to P naught. It's initial pressure which we had at some reference temperature. Reference temperature could be, let's say, under normal conditions at sea level, icy water, which is 0 degrees Celsius, and could be also boiling water at sea level, which is 100 degrees Celsius. So we can have these two reference points, measure parameters, either volume of liquid or pressure of this constant pressure, a constant volume thermometer at these reference points, and then we can calibrate our devices, thermometers. So pressure will be equal to P naught, let's say at 0 degrees Celsius, plus M well, not mass, it will be better to express in terms of density. So rho, density of this, let's say mercury, times G times H. height of this pillar. So that will give us pressure. So we will define pressure with the height of this mercury on top, and we will have something like this. We will have two reference points, for instance, that will be 0 degrees Celsius. Here will be 100 degrees Celsius, and we will have linear dependence between these 2 points. And that will for sure give us linear dependence. We will not have any non-linear behavior, which is really great for performing accurate measurement. Moreover, if we consider different gases, they will differently respond to increase of temperature. So what will happen? For instance, we will have different slopes of this linear dependence. However, if we extrapolate these linear dependencies between pressure and temperature towards some large negative temperature, they will intercept temperature axis in the same point, which is minus 273 degrees of Celsius. And that is absolute zero. So far we were operating with degrees of Celsius, but we also can operate, and that's mostly accepted and quite common in physics, to deal with Kelvin. So we can write that temperature in Celsius will be equal to absolute temperature in Kelvin minus 273.15 to be kind of accurate. And we assume that 1 degree of Celsius is equal to 1 Kelvin. To be more accurate in terms of determining the absolute, let's say in terms of determining Kelvin, it is actually calibrated between absolute zero, so T is equal to 0 Kelvin, up to so-called triple point of water. So this is some special phase state of water, which is a single combination of temperature and pressure, at which liquid, ice, and vapor can coexist in equilibrium, in thermodynamic equilibrium. And that is, for that triple point of water, temperature is 273.16 Kelvin. Or in other way, we can write it in degrees Celsius, it will be 0.01 degrees Celsius. So the difference between the triple point and the 0 degrees Celsius is very small. It's like 0.01 degrees Celsius difference. To be very accurate, 1 Kelvin corresponds to 1 over 273.16 of degrees Celsius. So in order to get the the range between 0 and triple point of water, in order to divide it in equal ranges, So 1 Kelvin is determined as 1/273.16. However, since it's so close to 273.15, that is not so different when we consider with respect to the 0 degrees Celsius range. So now, if we proceed further, let us see what is the relationship between expansion parameters of solids and liquids. So let me probably go to another slide so we have more space. And we can write the change in the length of, let's say, some solid material. We have alpha coefficient times initial length of material and times delta T. So alpha is this coefficient, thermal expansion coefficient, but so it's linear thermal expansion coefficient. And but that is true for change only in length. However, we know that if we have some bulk material, it will increase also its volume with change of temperature. So we can write that change of volume is equal to some beta, is other coefficient, it's volumetric thermal expansion coefficient, times initial volume, times change of temperature. So the question is how these guys are related with each other. There should be some correlation between them. However, it's not clear how exactly they are related. So if we consider some solid box with sides L, omega, and H, for instance, so these are sides of the length, width, and height of the box. Then we have initial temperature, T initial, and initial volume, V initial, will be equal to the product of L times omega times H. So at some temperature T initial plus delta T, we will have volume of this box, which is equal to V initial times plus delta V. So volume will increase if we increase temperature. So how we can express this V initial plus delta V? That will be equal to L plus delta L, then times omega plus delta omega, then H plus delta H. If we multiply all this, first we substitute instead of delta L, delta omega, and delta H, their expressions. So we will express them via this coefficient alpha. So we can write that L plus alpha times L times delta T. Then here will be omega plus alpha times omega times delta T. And the same for the height. Alpha H delta T. So now we can multiply all of them and take out from the parentheses the product L times omega times H, then we will have here 1 plus alpha delta T in the third power. So now we should remember that from algebra, if we have some a, b in the power 3, a plus b in the power of 3, then we can express it as a in the third power plus 3 times a in the second power times b plus 3 times a times b in the second power and plus b in the third power. Okay, so according to this transformation, we can also express our equation. So that will be, so this stands for initial volume. So we can write V initial. And here we will get unity plus 3 alpha delta T. Then we will have 3 plus 3 times alpha delta T in the second power and plus alpha times delta T in the third power. So now we need to mention that fact that thermal expansion of materials, we already discussed this at the beginning, it actually is very small. So in the range of small change of temperature within few dozens of degrees Celsius or Kelvin, we will have quite small change of the length of our solid body. So for this purpose, we can write to highlight this, that product alpha times delta T, assuming that delta T is not very big, is smaller, like much smaller than unity for most materials. And in this case, we can neglect with second and third order of this product alpha delta T because it will be much smaller than just alpha times delta T. So taking this into account that this alpha times delta T is actually a small value, we can write that this will be with certain approximation equal to V initial times 1 plus 3 times alpha times delta T, because other terms in second and third power, they will be much smaller than this first term without in the first power. So now let us write it down on the next slide so we have less crowded picture. V initial plus delta V will be equal to V initial times unity plus 3 alpha times delta T. So now if we divide this by volume, initial volume, we will get unity plus delta V over V equal to 1 plus 3 alpha delta T. So 1 and 1 we cancel out. And from here we can write that delta V, change in the volume, is equal to 3 alpha times V initial, this is initial volume, initial times delta T. So you see that initially we wrote that change in volume is defined as some beta coefficient times initial volume times change in temperature. And now we got for this delta V another equation in terms of alpha. And we see from both these equations that beta, the volumetric change thermal expansion coefficient, is equal to 3 times alpha, which is a linear thermal expansion coefficient times 3. So this relationship would be useful because sometimes you are given one parameter and need to operate with another in terms of solve a certain problem. So you can make a transition from one to another. And this is a clear example how we express volumetric thermal expansion coefficient in terms of linear thermal expansion coefficient. Okay, guys, so I think that with this we can finish our today's discussion. So we will mention a bit about water thermal expansion during next lecture, but that will be short part, and then we will focus on microscopic description of an ideal gas. So during our today's lecture, we introduced the thermodynamics as the field which is dealing with change of temperature and amorphous state, sorry, like the state of material, either solid, liquid, or gases, when there is some transfer of heat between different parts of the system. Introduce temperature, how can be measured temperature, like liquid thermometers and thermometer with constant volume, and also found the relationship between the linear and volumetric thermal expansion coefficients. If you have any questions, you're welcome. Task with this topic will not be on midterm exam 3. No. Midterm exam will not include this material. It will be only until the and including acoustic waves. Okay, you're welcome. Okay, guys, then thank you very much for your attention and see you on Wednesday. Take care and have a good day. Bye-bye.
Thank you. Goodbye.
Bye.